Good afternoon, everyone. Welcome to this first seminar. This is the first seminar before the school that we start tomorrow. So welcome to Barcelona, let's say, even virtually. So today, as you have received in your email, there is a first seminar before school. It's delivered by Mario Cuoco. I will introduce him now, but just I want to start by saying that this is a third edition of the school. It's a series of schools on frontiers in material science and context matter. Previously, we have organized other schools. For instance, in February, we organized, February last year, we organized this school on ARPES. And more recently, in December last year, we organized a school on orbital currents and solids. So the school that is starting tomorrow is, I don't know, maybe it's not working. Maybe. Okay. Now it's working. Okay, so the school starting tomorrow is on Rashba and Berry physics in quantum confined systems. There are three lecturers. Annika Johansson from Max Planck Institute in Halle, Germany. Mario Cuoco, who is giving the seminar today, coming from CNR Spin at Salerno in Italy. And Andrea Caviglia, coming from University of Geneva. So then today is my pleasure to introduce Mario Cuoco, who will talk about signatures of spin orbital chiral metal. Mario is a researcher at CNR Spin in Salerno, Italy. He's a well-known expert in condensed matter physics, in correlated systems, topological materials, orbital, spin, lattice degrees of freedom. He has participated and also has supervised many European projects on different proposals regarding these topics. And today we have the pleasure to hear about, let's say, the latest news about these correlated systems, especially spin orbit chiral metal. I understand from the abstract that one of the focus could be Strontium-Brutonite-based quantum materials, that it is very interesting material. There has been a lot of debate over the last years, and I think will be very interesting to hear about that. So thank you very much, Mario, for delivering this talk and also the school. So I give you the floor to start. Thank you very much.
Okay, thanks a lot, Gervasi. Thank you very much. Should I remove this?
Yeah, sorry.
Okay. Yes. What is it? Here.
Yeah.
Already open. I will make it there. So I don't know. I think they hear from the remote. I think so, right?
In principle, yeah.
Okay. If they don't hear,
if they do not complain,
so if nobody complains, either they don't hear or they're sleeping. Can I keep it informal, because otherwise people start to sleep and then you know, it's not nice. I mean, okay, thanks a lot, Gervasi, and it's a pleasure that maybe we get rid of this stuff.
sorry.
Okay, yes. Okay, yes. Thanks a lot. I mean, for the invitation of the school and also for this opportunity to share his latest news about this research. And okay, so what I will tell you today, this is a very recent result we obtained, and the story is in this slide. So I think I will take the few minutes to explain what we did and why. And then we'll go into detail. So basically, the question was how you can probe not conventional ordering of electronic ordering. I mean matter. And we we just sucks. I have to be honest, we accidentally came through this observation. And I'm also happy to tell the story that I'm a theorist, but I'm often, also attending the experiments. I was interested during the experimental beam time at Electra. So in Electra, they have a very nice setup. They can use light. They can do a photoemission experiment. They can use a circularly polarized light, so they can send light with the right hand and light and left hand anticlockwise electric field rotating like here, and then they can measure the photoemission, but they can select the spin of the electrons. So this is really it's a spin resolved angular resolved photoemission experiment with circularly polarized light. So basically, you expect, that since these right and left hand, they carry some angular momentum that you can excite different spin up and down, but there should be some symmetry properties at the end. If, for example, time is conserved or you are in a mirror plane, so this probability should not be completely accidental. And the general question, I will try to convince you that if you do this kind of experiments, you can probe non-trivial electronic ordering and eventually current phases. Okay, so let me start to tell you what are the people. So, okay, there are many people and about this work. Federico Mazzola is a researcher in Venice. He was the main driving person of the ARPES experiment. And then my colleagues in Salerno, Carmine Ortix and Marisa Mercaldo about the theory, and Wojtek Brzezinski in Krakow, also about the theory, and also my colleague in Spain about the crystal growth of the materials, Antonio Vecchione, Tatiana Fittipaldi, Anita, and Fabio, mainly on the experimental side about the growth of the materials, characterization, basic characterization of the materials. Okay, but there are many more people. So this is so what I will present has been published recently, and there are the group in many groups from Italy. It's really a strong imprint of Italian people in Milano, in Trieste, and then there are other groups in Denmark, in France, and in South Korea. Okay, so this is the content. I would like to tell you at the beginning something very basic about the symmetry breaking with the spin and orbital degrees of freedom in, let's say, complex materials. And then, as Gervasi was anticipating, so what I will tell you is more general, but we found a case, and I will explain you this case of why it has the right states to be probed. And the Stronzi-Rudalate was the case with a weird magnetism on the surface. And I will go through these unconventional phases, which have been, we propose, to explain the observations. And in particular, about this photoemission experiment, I will try to convince you that this is really an evidence. So we got an evidence that the metallic state on the surface has a spin orbital chiral properties. And I will explain you what it's about. Okay, so let's start with symmetry breaking. So I think that we have electrons around. Okay, also the lattice for the moment. Let's forget about lattice. You have a charge, you have a spin, you have orbitals. So this is a typical. I know that you are familiar with oxides. So and these degrees of freedom can order in real space. They can make a pattern, right? So like charge ordering, charge density wave. They can make magnetism like ferro, antiferromagnetism, or whatever. Again, and orbital also can do the same, right? You can have orbital order, and these things that can come together. So this is what you typically learn also in your education, right? That you have a charge which is a scalar. You have a spin which is a pseudovector. You have an orbital which has a quadrupole. Again, is a charge, anisotropic. And is also a pseudovector, is an angular momentum, which can order. So this is a typical conventional ordering that you learn in Landau framework. Is it all like that? There are other types of ordering which are a little bit different. So these are, the electrons can make currents. So all these, I told you before, is basically is all the parameter is degrees of freedom, which takes an amplitude locally and orders spatially. But the charge can have a current, and this is usually usually what is named loop currents. So electrons can go around in your lattice. I make just a basic sketch on a square lattice, and this has been historically proposed for cuprates and other materials. I mean, these are kind of, you know, it's really current like you learn in basic electromagnetism, but on an atomic scale. But now, okay, once you think about charge, you can also have spin, of course, yeah, spin current. So, and you also can have orbital current, which links to what you learn in the other school. So what is the main difference about charge current and this type of currents? That the charge current is a current which breaks time, while these currents, they are neutral. So basically spin current, spin up goes to the right, spin down goes to the left, charge doesn't move, you are just accumulating angular momentum. So spin current and orbital current, they transport angular momentum, the charge doesn't move. So if I have these degrees of freedom, what can I do more? I can do more, I can have a orbital quadrupole current. So because, yeah, the charge can move, but it can also move only in an orbital selective way. So orbitals in these XY type of anisotropy can make a loop, and in other orbitals can do different, for example. So this means that you have a quadrupole correlation between the angular momentum. And then, okay, since these electrons, there can be also a spin orbital quadrupole. So electrons with a spin can move, making flowing in your lattice. Okay, let's forget for a moment, I mean, about whether the pattern is homogeneous or it breaks translation, but it can carry quadrupole the charge. So the charge is very basic, right? But in a crystal, it's more likely that your electrons will have some anisotropy, so that it will be quadrupole loop current or spin orbital quadrupole if spin and orbital degrees of freedom, they are coupled. So now, what is interesting about these currents? So basically, so this is a summary. So of what you can have. I mean, basically beyond that, you can. I mean, it's over. I mean, so we cannot make more than that. But these guys down here, these are very interesting. Why? Because since they carry a quadrupole, the quadrupole can transform in a non-trivial way when you make a mirror and rotation. So for example, if I have an Lx and Ly, so if I make a mirror, you know, the pseudovector, when you put a pseudovector, an angular momentum in front of a mirror, the component which is perpendicular to the mirror doesn't do anything, and the component which is in the mirror is changing sign. So now if I have this current that carry, for example, Lx, Ly quadrupole, if I take the mirror Z, nothing happens. But if I take the mirror which changes X to minus X, one of the guys change and the other one not. So this means that these currents can be potentially can break other symmetries of your crystal, and in principle can break everything, can become chiral. So they break all the mirror, they break all the rotation, and you get a state which spontaneously develop chirality. So now, so we have this list of states, and you say, okay, but how we can detect that this guy is very elusive. Also because while these magnetic states, when you order magnetically, you see really magnetic moment. These flow current, they make mostly flux, which is a tiny magnetic feature. Is different from the ordering of magnetic moments in the crystal. Okay, so now this is the intro, and I will come back to these phases. So the basic question, okay, can we have some basic signature to get into these phases and these ordering, which are not standard, these are current flowing in the crystal. And so is there a way accessing the spin and orbital features of the electronic structure at the Fermi level? We can understand whether this ground state sustain this type of ordering? So these are the questions. Okay, so we tried to answer this question. So, but we took a case, transglutamate, which was always was telling us something is going on, and I will start to tell you why we choose this case. I mean, yes,
Can I ask you a trivial
of
question?
course.
So why is this the ground state of the system, and why the state without currents is not the ground state?
Yeah, this is okay. This is a good question. These phases are typically, of course, are broken symmetry states. These are stabilized by interaction.
So
Exactly. So it's exactly like you ask why you get the magnetic phase and the paramagnetic phase.
then
So this is a
which
yes.
interaction?
Yeah, Coulomb interaction. So, but not local Coulomb interaction. You need and so if you treat the problem in a weak coupling, you need a nearest neighbor. I mean, so a short range Coulomb interaction. But this can also, if you go beyond the weak coupling, you can get it also with the local Coulomb interaction. So you need interaction. So this is the basic answer. Okay, let me try to convince you that glutamate is a good case. Okay, in this line, I just want to tell you there are many information. So this system in the bulk is not magnetic. So there are plenty of observation. Okay, there is a long story about glutamates. Okay, probably most of you have heard of the recent discovery that the P wave is not anymore the superconducting phase because there were some issues about the night shift. But these materials seems to be very close in stability because okay, if you grow the cubic phase is ferromagnetic. So this is a monolayer phase, it's a 2-1-4 phase. So if you look at the neutrons or basic measure of the night shift, you see some enhancement, but you don't see a real transition. The bulk is not magnetic. But what I want to tell you, the surface has something. So actually the surface has something, there is something going on. And this has been recently shown by muons and by STM. And let me start on that. So the point that the surface has some weird magnetic features. So let's see about the muons. Also, this was a collaboration with people in Salerno and not in Salerno. I mean, so I want to keep it short about the muons. So basically, muons, what is doing? I don't know whether you are familiar with muons. Basically, muons are so you inject muons on material, and the muons is decaying. The positron is scattered, and since the positron is a relativistic particle, so the spin and the momentum are parallel. So that if you detect where the positron goes with the detector, you will know the spin. So then what happens? The muon is implanted in the crystal. If there is a magnetic field around the muon will start to process around the magnetic field as any particle with a spin, and then at some point it's decaying, and this positron is expelled. You have all your detectors, you detect these in real time, and you extract them in some time dependent of this amplitude, and from that you extract the magnetic field the muons is feeling in the crystal. And then okay, so this is one slide. But in the experimental part, I mean, this upturn here is an evidence of a transition. Something is going on, so there is ordering below this temperature. But the magnetic field, which with the muons is a feeling is a 10 Gauss, 20 Gauss. So you have something which is ordering at 50 Kelvin with an ordering moment of 10 Gauss. So which is 10 to the minus 3, 10 to the minus 4 Bohr magneton. So any theory you can do with the spin conventional magnetism will never get that. If you get 50 Kelvin, the magnetic moment will be comparable on the same scale, right? So then, okay, we thought, what can be? So these are the main two things which were really telling us that something was going on, which was quite weird. So something which is ordering at 50 Kelvin, but the amplitude of magnetic moment is less than 10 to the minus 2, 10 to the minus 3. Very abnormal. Then we thought, okay, maybe there is some loop current going on. But also the loop current tends to order and gives 100 Gauss of flux, right? So why is so small? And now comes again the something which is which is linked to this loop current. But before that, there were these STM experiments, which also, this is also nice that the guys that when they published this experiment, I mean, they didn't mention our work on muons. But basically, they measure on the surface these conductance, and they see that first of all, there is a breaking of C4 of the conductance. You see these stripes very, very clearly at these 3.5 milliV and 4.6 milliV. They have a different pattern. And if you apply magnetic field, this is really very interesting. Some of the peaks in the conductance they split, and the rest not. Okay, then you say, okay, this is a Zeeman splitting, blah blah. But okay, so but why some peaks they split? So these are all electrons. They are all spin 1/2, right? So so this is definitely is another evidence that there is some magnetism and some ordering going on the surface. So what we propose that there is this loop current phase. So why we propose this loop current phase? Because it's the only way we could accommodate low magnetic moment, high temperature, and the breaking of C4. So, and these are actually, to understand that, you have to really go in the details of the orbitals which are involved in the electronic structure. So the electronic structure of ruthenium oxide has these dxy, dyz, dxz orbital, hybridizing with the oxygens around. So now, what you can have these you look at this octahedra loop current, and you can have different type of flux. Either the current is anti-clock or is clock, right? We call it plus and minus this flux. If you take this current flowing like that, opposite. And these are actually, what is interesting is that you can have a negative and positive magnetic flux, but this can be orbital dependent. So this is actually the key point. If it's orbital dependent, basically you can have two possibilities. Either all the orbitals, they choose the same flux. So xy is plus and the z orbitals plus, minus, minus. Either the orbitals, they cooperate, making the same loop, or they anti-cooperate. When xy is plus, but xz is minus in the same plaquette. So these two phases we put in the model, and we found that the minus is more stable. This is a free energy as a function of the flux generated by the loop current, and you see that the minus is more stable. And this is energy gain is 10 milliV, which is our 70 Kelvin, 60 Kelvin. But the flux you get, since there is a cancellation between plus and minus, the flux is like in a ferromagnet, is very tiny. You don't see anything. So this is a state which doesn't seem to have any magnetism, but still is ordering. It's a very tiny magnetic moment which orders at high temperature. Okay, so but then we say, we have this material in mind, something is going on. Can we see something with photon emission? And everybody say, okay, look, so if there is magnetism, you should measure dichroism. So this is, of course, I mean, is the first thing you ask. And there are a lot of degrees of freedom. Is a charge, loop current, spin orbital degrees of freedom. Can we look at that more directly? Because all that I'm telling you now is, okay, is matching the phenomenology, but so can we really see that? And then we went to this photon emission experiment. So basically, if you have something which is magnetic, breaks time, you should see dichroism. So what you do, you go with the right hand, you go with the left hand, and you measure the difference. And this you can do as a function of k, right? So unusually at k and minus k, this dichroism is changing sign, basically, right? But now in this experiment, you can do also, you can make left up, left down. You can also filter the spin. This is something really crucial. And you can do the same with the right. So in principle, I can define a spin resolved dichroic signal in the experiment, right? I can have spin up, dichroism, and then also spin down. So then the next step is the following. Basically, if you are if you select two momenta in the Brillouin zone, which are time partners or mirror partners, right? So then this quantity cannot be whatever. They should be related because when you make a time reversal, you go from k to minus k, up goes in down. So in principle, what I measure at k, if I go at minus k, I should see something which is more contains this symmetry, is reflecting the symmetry. Okay, was the experiment. The experiment was done by making all these polarized, looking at dichroism, spin resolved dichroism, and looking at momentum which are symmetry related, k to minus k, in a mirror line, right? And these are the experiments. Okay, this material has a Fermi surface, is beautifully shown in this plot. I mean, there are three. If you neglect for the moment these folding due to the fact that it's an orthotropic reconstruction, there are basically there are three pockets. So this one is a hole-like and two are electron-like, and this in the middle these are shadow bands coming from the folding due to the reconstruction. So then the people they made this cut, they choose this slit, all this kind of you select your plane, your scattering plane, you sit in the perpendicular to this line and you scan, and you look at this process of photoemission, spin, and dichroic results.
So the exciting light is just UV.
This is a X. It's done at the synchrotron. Yeah.
So are you looking for some resonances also?
No. This is it's done with X. So it's in a range of energy because you want to. You are not really surface sensitive. You are a little bit. You can go a little bit below the surface. I think even if the surface is very good.
Is it important to get the effect?
I think it's important because what I learned, but this is what they told me. Actually, to have a good circular control of the light in lab is not easy. While at the synchrotron, they really have a very good. I mean, so the polarization of your photons is highly controlled. So this is what they told me, but I cannot confirm it. Maybe you know better than me.
And that works in some specific windows.
Yes, right. Yeah, because they have all these modulators, all these things, and they work very well with the synchrotron, right? So, and then the part which is challenging is the spin. They have this spin detector, this mode detector for the spin that you have to calibrate. They calibrate with gold, then they do experiments, they clean, they calibrate, and you get always the same. This is something which is really is time consuming, right? And this is the dichroic. So this was the first thing which was really. So they measure the dichroic, and the dichroic is always is in a material which doesn't break symmetries. Is always quite good. There is red and blue at k minus k. So because if you reverse the momentum, and things are time conserving, your dichroism should change the sign. So this is what you observe. And the first thing is that the dichroism is conventional. There is no magnetism. And you see this is more or less what you get. I mean, but then you look at the spin resolve, and the spin resolve got crazy. So the spin resolve, you got this asymmetry. You make k by k up and down. If you want, we can look at the detail of the experiments. But you see, this gray part is a dichroic, and forget about what you have close to the Fermi level because there is some counting statistics, so it makes a little bit things not easy. But you see that here all these reddish and bluish, which are the spin resolve part. So up k minus k and down, they are different. So what they observe is basically that your decrease stays in some windows of error in between 10%, but the spin dichroic difference at k minus k can be large 30%, 40% different. So which is not, so there is an anomaly when you look at the spin resolve decrease, which is not compatible with the fact that your system doesn't break time reversal. So it's time conserving. So if time conserving dichroism should be trivial, but the spin dichroism should also be trivial. So that these two things are not compatible. Okay, so then this was the main, so basically dichroism seems to be symmetric, so it doesn't seem that you have any magnetic ordering, but the spin at k minus k So when you compare K with minus K with the same spin, opposite spin, you get an anomaly. So there seems to be that these when you use this polarization light, and you look at the spin, there is some sort of optical to spin coupling, which is of course coming from the electronic states you're probing. So now, okay, we say, okay, can we understand that? Okay, this is one slide. I will tell you what you measure with the dichroism and with the spin dichroism is basically the orbital moment of your electrons and the spin resolved orbital moment. Okay, you can go through it. I don't want to bore you, but basically, these you make a typical scattering with the vector potential. You make your initial state. The final state is just electron, which is expelled by the material. You analyze that with this Hamiltonian, and you extract this amplitude and these G factors. When you calculate these G factors, this cross G factor is related to the contains the U, which are your translation invariant part of your block states, and this U part is linked to the orbital moment. And then if you want to measure the spin resolved part, so this is the expression of the spin resolved part. So the most important part is this average over the block states. This other part is more coming from the kind of geometric factors, I mean the gradients, which are not relevant in the, so they are symmetric at K minus K. So basically, so the focus is on this quantity. You measure orbital moment and the spin resolved orbital moment. Here, if I put up plus here, I project on spin up. If I put minus, I project on spin down. Okay, then, so what we said, okay, we were biased by the other experiment with this loop current. And I was like, okay, let's plug in these states and see whether there is something going on. And we were lucky, I will tell you why. But we look at this spin dichroic, this dichroic part and the spin dichroic part of our electronic states when we break the symmetry. Okay, this is the Fermi surface. This is theory, but looks very similar to experiments. And we scan one direction of the along X. We take 2 points, and we evaluate this orbital moment of our states. There are different bands here. There are many bands, and is an index of the band. You can look at the orbital moment at K minus K, and then I can do the same with the spin projection here, 1 plus, 1 minus. So what I will call it LZ plus, LZ minus. So these are the two quantities which I want to compare with experiments. So then what I do, I start to include this quadruple current in my problem. I assume that there is a flow of quadruple current along a given direction. This direction is the direction of where I'm measuring the photon emission. And this is what you get. Now, in just a few seconds to see what is the meaning of this figure. So in the same figure, at the given K, you plot the value of LZ K and minus LZ minus K. So the same, so the dichroism at K and the opposite value at minus K. So if your system is conventional, these two things should be the same. But you see here that the dichroism is completely deviates. There is no, symmetry. And also the spin dichroism, these are two bands. And also if I take this spin dichroism also, is completely asymmetric for this orbital quadruple current. But if now I take the spin orbital quadruple current, which I was mentioning before, this was really surprising us because this state breaks time, but the dichroism is completely symmetric. So LZ at K is exactly equal to minus LZ at minus K. So although there is a symmetry breaking, this flow of this spin orbital quadruple current is has a no dichroism. But only the state which has this, look at the structure. Here there is I take Kx, and then I have these components which are like L cross sigma. So this Ly sigma z minus Lz sigma y. So these spin orbital correlation are chiral because if I make a rotation around z, z goes to minus in itself, by Ly goes to minus Ly. If I do a mirror in x, this kx minus kx is broken. If I do a mirror in z, Ly goes in minus Ly. If I go do a mirror in y, sigma z goes in minus sigma z. So basically this type of current when the electron moves and the spin and orbital, they are cross vector, they are chiral spin orbital, chiral correlation with these special properties that they don't carry any decrease. But, and this was, if I look at the spin decrease, they have a spin decroic anomaly. So when I look at the spin resolve amplitude, you see these orange and blue, they are different, which means that what I see at k and what I see at minus k, they are not equivalent, and this is a band dependent. This is exactly what they observe experimentally. So then you say, okay, but is it possible to get other phases? Yes, we put the magnetism, antiferro, ferro, spin ordering, whatever. You get decreased and the spin decreased. No way. So this was the lucky part. The only phase we could find that was giving you very small decrease, almost no decrease detectable experimentally, and a huge spin decrease is this phase with a, is a chiral, spin orbital chiral metallic state. We named it spin orbital chiral metallic phase. Okay, how to explain this? There is a sort of dynamical symmetry in this phase. You can understand if you analyze the spin orbital torque in the problem. I don't have the time, I don't want to go into all this detail.
Maybe
Yeah.
basic question, but the spin orbit that you're considering here, is it something in surface related, or are you thinking that this is also about phenomenology?
Okay, the question is the spin orbit you are considering is only in which spin orbit? The atomic spin orbit or the ordering of the phase?
Both.
Okay, the spin orbit we consider is the conventional atomic spin orbit. But this phase we are considering here with this, this type of current. So this is coming from the Coulomb interaction. Is a spontaneous symmetry breaking on the surface.
So this is a manifestation of spin orbit in the presence of this Coulomb interaction that is breaking the symmetry. Okay,
the question is, this is the manifestation of spin orbit, but look, this is a cross vector. It's not, spin orbit is L is parallel to S. This phase, L is perpendicular to S. So you gain energy by moving electrons where they want to keep an orbital moment and the spin, they are not collinear. So this somehow goes against the spin orbit in a sense, but is cooperating because at the end the dichroism is conventional. You don't see, so when you average on the spin part, you don't see the magnetic symmetry breaking, the time resistance symmetry breaking. So it's very subtle, but there is a cooperation with the spin orbit, and you see it when you go in this. If you write down the torque equation, so you will see that there is a sort of cooperation between the spin orbit coupling and this kind of spin orbit correlation.
Yeah, but somehow I was under the impression that this magnetism that you were measuring with muons was a surface phenomenon.
Yeah, this is on the surface, yes. The question is whether this is a magnetism on the surface. Yes, this is something which happening only on the surface. Yeah. Okay, why are you asking why is only on the surface? So one reason is that this material is tetragonal in the bulk, but is orthorhombic on the surface, has a less symmetry, as a reduced crystalline symmetry on the surface. So the second reason is that, of course, these are layered materials, and the surface, if you want, is mimicking the two-dimensional part of your system, and you have a breaking of inversion only on the surface. So if you ask me what is the difference, I mean, between the surface and the bulk, there is orthorhombic reconstruction, so there is a staggering and breaking or inversion. And now, actually, to me, this is really important. I mean, I don't understand deeply. I mean, maybe there is no unique theory about that. But it's interesting that they measured, I mean, in one of the, if I can go back in one slide, which I was really flashing, experimentally, you know, this experiment, when they apply the axial stress, look at it, you get the spin density wave, what they call it spin density wave. These are bulk muons. So they measure magnetism at 6 Kelvin, below 6 Kelvin. Now, when you apply the axial stress, basically you are making more orthorhombic all the crystals. So, okay, my feeling is that at zero, only the surface has this weird ordering because the bulk is too symmetric and you cannot see it. And when you apply pressure, you can make it also the bulk crystal ordering. So, and, but without, so you break more symmetry, you reduce the crystalline symmetry, you get this phase maybe built in also in the bulk. But this is, okay, we have to overcome, I mean, the obstacles of the people believing other things. I mean, okay. Anyway, but this idea, there is a surface bulk story which cannot be completely neglected. I make a comment on that, actually, that there is now academic comment at the end of the conclusion. But so what I will try, so now I want to add a few things about this phase. One is that if you include this surface reconstruction, or you can have other zoology of these phases, still you keep the phenomenology. So decrease is very small, spin decrease is very large. And these, to our understanding, these phases are the only phases, chiral phases, which they have this current, loop current with the spin and orbital degrees, carrying spin and orbital correlation, chiral correlation, are the only electronic phase which can explain this phenomenon in the photo emission, to our knowledge. If you have other proposal, we'd be happy to get that. Okay, so what are the, I come to the conclusion and I make some comments on that. I mean, so basically, if you exploit this spin resolved photo emission, you can really access to non-trivial ordering in and you need to combine this circularly polarized angular resolved photo emission, because you need to look at K and minus K. You have to use a circular polarized light, and you have to extract spin up and down. And this allows you to have a new view on chiral electronic states, because you are using somehow, you are exploiting the chirality of the light, and you are looking at the spin, and if your system has a, so the chirality of the light is an orbital moment. You expand the spin, you are looking at some chiral correlation between the spin and orbital part. So this is it. And this state, if you have this feature, it is the only phase it can explain this phenomenology. So then these are, okay, I showed you for the Strontium root arrays, but this applies to all systems which can have this symmetry breaking on the surface, or the bulk in 2D. So you can have all the 2D materials with the chiral electronic ordering, and using this spectroscopy, you should be able to understand more how the internal degrees of freedom they are correlated. I mean, whether they correlate, because chirality can also come from breaking of translation symmetry. So here, this phase can be also a metal without breaking translation. It is the chirality of the spin and the orbital angular momentum which sets in the anomaly. You don't need to have extra symmetry breaking, right? I don't need to have ischemias. I can do it. It's a Q0 ordering. Okay, these are the other, the other message, take-home message is basically if you access this L and S, of course you can definitely get a lot of information, and you can probe it in the Boolean zone. I mean, at all momenta, basically you can access how spin, orbital, and crystal symmetries are linked in a correlated fashion. And so a comment which I want to make is that you one may believe that that this is only happening on the surface where you break inversion, but this phase also in the central symmetric environment will appear. In that case, the dichroism should be 0 by symmetry, because if you don't break inversion, I mean you have degeneracy, Kramer's degeneracy at all k. But still, if you access the spin up and down, you are able to separate. Even if you are up and down degenerate state, but I can expel up and down separately, I can also look at what are the correlation, even if there is degeneracy. So this will be even more striking. The material is completely adichroic, but you see the spin resolved and you see something. So this is really counterintuitive. So one final comment, which since is about the connection with the superconductivity. So this is my so I want to make a 2 minutes comment on the superconductivity, because people now they are so what I'm trying to push in the community, this idea that this material on the surface is magnetic, is a weird magnetism, and then the bulk becomes superconducting. So now they see all these anomalies about when you look at the breaking of thermorestal in the superconducting state, they have an anomaly when they apply pressure. So the TC and the temperature of the onset of the thermorestal, they split. But when the thermorestal split temperature, at the thermorestal temperature, they don't see any anomaly in the specific kit. And I say, okay, fine. If it's a surface effect, you break the symmetry on the surface. Behind you have a superconductor. This magnet is dipolar field. They can go through, you will see something which is breaking time, but you will never see in the specific kit because it's just a surface. Specific kit is measuring everything, is a bulk property. So I think that this observation contains hints to understand the origin of the thermorestal symmetry breaking in the superconducting phase. So I think that I know that they don't want to listen to that, because this is again, I mean, bulk superconductor is not P wave, it's not a chiral because it breaks time. It's just as good as any superconductor, but it's a surface which is anomalous, which is imprinting something in the bulk. So okay, I don't know whether the community will get it or not. There will be new experiments to try and okay, I think I finished. Sorry, I had other extra slide. With that, I finished. Thanks for your attention. Yeah. I made it in time, probably.
Yeah, thank you very much, Mario. I think it's a very interesting perspective on this material. Very subtle correlations. I think it's a very interesting perspective. So let me see if there are questions. Also, people online, if you have any question, because there are several people online, you can drop a question in your chat line. So please feel free to drop a question by the chat line, please. So is there any question here?
I have a small question. Yeah. Usually, spin resolve arcs is used to measure the dichroism or the spin splitting in some specific band of the material, in topological insulators or things like that. This is very focused on the orbitals. Are there some splitting of the bands at the surface?
You cannot resolve the splitting. Maybe. Yeah, the question is whether, okay, the question is that usually spin resolve arcs without dichroism is used to access, to probe, I mean, the spin texture of your electronic states at the Fermi level, like you do in topological insulators, or in general, you know, these altermagnets, recently, other materials, you try to probe these spin textures, right? So here you don't see that the spin splitting is very small. You see that the spin without the dichroism, they are different. You see some spin polarization, but is small. You can resolve the splitting. So So they are not, because this is metal, right? It's not that you are close to gamma and you have just your pens, you see clearly this splitting and so on. I mean, you are very far from gamma, and yeah, you don't. The splitting is more, but you see that up and down they are not equivalent, right? So which is indication that something is going on in the magnetism. But the decreasing, I mean, you know, if you measure the topological insulator, the decreasing will be again blue and red, right? And then you will see this. But if you measure the spin decreasing, you will see again something which is, you know, the same. It will be conventional because the time is conserved. So here, when you look at the spin decroy part, you see the anomaly. Yeah, I don't know what, so you don't, basically you don't see the texture of the, there is no texturing, you can resolve the texture, if this was the question. You don't see the split, there are no split band, you don't see the split band.
There are some difference because there's a difference between the polarizations of the light.
Yeah.
Also,
Yeah, there is a dependence on the polarization.
A difference between the spins, also change.
So basically, so the dichroism, when you change K to minus K, it changes sign. And this is coming from time is a time reversal symmetry which does that. So then if you take the dichroism with spin up at K, and you go at the dichroism spin down, because the time is also making up to down, you should see the same. And this is what you don't see in the experiment. You know, this is what, yeah.
Question. Thank you for the talk, which was very
Thank you.
mind blowing to me. But anyway, I have a question about more the material science. No? If I well understood, you talk about a difference between the bulk and the surface in terms of tetrahedral and octahedral configuration of the material. No? Indeed, you consider the T2G state, or the DX, and so on. Just random question. So if I have a material which is fully octahedral and I look at the surface.
Okay, no, the question is about, okay, sorry, maybe it's a question of language. So you're asking tetrahedral and octahedral. No, the difference is tetragonal and orthorhombic. Yeah. Okay,
Yes,
so just to be, so then the question is everything is orthorhombic?
Yeah.
Yeah, in principle, is everything is orthorhombic can be bulk state.
But if I look at the surface.
Yeah, the point that now, okay, the question is probably, so how I can access the bulk? In principle, I can use, okay, this is probably beyond the reach now. I can use a light with a high energy. So this is also done at the synchrotron, right?
Yeah.
You can, if you increase if you use a X-ray, soft X-ray, you can go deeper below the surface, right? So this, for example, is what is done for LEO-STO, right? You use a high energy light, you go below the insulating substrate, you can measure the interface, right? You can do that here, but the point that you lose in the statistics for the spin resolution. So I think that, so the question you ask, how can I know whether I have a magnetism in the bulk if I cannot access with the photoemission?
Also, but my question was also, I can choose a different material which is done all like your surface. Like the bulk, like all my material is done, it has the same symmetry of the crystal of your
Yeah, sure, you can.
And I can sense just the surface of this material done, all the same structure, and is that like the SVO?
It can be for any material, yes. In principle, you can do on any material. So the experiment.
In principle, everything that has this kind of
exactly.
splitting at the surface.
This kind of features in the photoemission, right? The dichroism is.
I'm just trying to look at the point that reverse. What are the
materials?
Yeah, the ingredients that I should have to see this effect. Like, you know.
Okay. What you mean? Which type of material?
Yeah.
Yeah, I think that, okay, so this is a good question. So I don't have an answer on, I mean, there is no recipe. I think that which material, so the point, okay, but the point I want to make is the following. Now you have, you know, now you have a new way to, so at least we establish that if you have a conventional decrease, and you may, all the materials which they don't look magnetic, because you make decrease on the surface, you don't see the decrease. They are good candidates, potentially. Because, you know, if you have a weak magnetism on the surface, or on 2D materials, right? And this magnetism is not based on strong ordering of magnetic moments. So then your dichroism will not be zero, right? So these cases could be good candidates. And you have to use a probe which allows you to detect now a phase which is non-dipolar, which has this current, loop current phases, right? So this is, I mean, now you have a new, you can take all your materials, which in principle is, okay, these are not magnetic on the surface. And you go with the spin result, and you see, if they keep this dichroism zero, but a huge spin decrease, because this experiment has been done on other materials, which are conventional, right? And they didn't find any anomaly,
For instance, with which materials?
Actually they did on some I think it was a 2D materials. It's Federico Mazzola had another paper where they use this spin dichroism to detect the spin berry curvature close to gamma.
So not in oxides.
Not in oxides, no. It was I think it was yeah, I don't remember now the material, but not in oxides, yeah. Yeah, in principle, yeah, I think that all the materials which 2D they look unconventionally, so they don't look magnetic. They may have this weird ordering inside. So which I mean, to probe it, you have to use these other yeah.
But if I understood correctly, the idea, you need this a quadruple order.
Yeah.
So that means that you need, for instance, a T2G population, for instance, T equal to 4. In order to have a angular momentum,
Yes.
that is the G, the total G, the G in the GG language, let's say, it would be something like G equal to 3.5, let's say. So
Yes.
if your total angular momentum is 1.5, maybe this is not.
Yeah, if it
exactly.
doesn't, you're asking if it recuperates, you
Exactly.
will not get that because there is no angular momentum to use for the orbital
Because you
part.
have just one hole.
Spin one out
Yeah.
and that's it.
So
And then you can have the orbital part, it can come from the K-dependent part.
Mhm.
So then it means that you have to reconstruct.
Yeah.
So with the breaking translation. So then, but these are then will be more visible also because you will have a super lattice.
Mhm.
So in this case, if you have an orbital momentum which is coming from your internal degrees, you don't need to have a super lattice, which anyway is cost and I mean it's more complicated to establish as ordering, right? But yeah, then it will work for all T2G materials. So all materials which have high spin orbit coupling or they have the potential, but okay, we don't know.
But for instance, not the T2G materials and the high spin orbit coupling, like in the case that what I have in mind are not coexisting, no? I have the T2G material, but I have a very low spin orbit coupling.
Okay, if this, for example, you can have.
Oh, sorry?
If this, rhodium, iridium,
yeah.
rhodium,
No, I
niobium, tungsten, all these materials are niobium, tungsten, rhodium, all these.
The spin orbit coupling is a.
It's very large, yeah.
Yeah,
It can be.
is a key ingredient, no? I should.
Yeah, but also in titanium or vanadium, you have a little bit of spin orbit coupling and it makes unquenched orbital momentum. It's not huge.
Yeah.
So then, okay, the other thing is that you can use, as you learn in another school, you can use the breaking of crystalline symmetries to unquench the orbital moment. So orbital Rashba, another interaction. So if you have a low crystalline symmetry, you can have also in the titanium you can get high orbital currents. So I think that okay, these are I think it's a good question. So the question, I mean, you always think that if you want to have a high orbital moment, you have to have a heavy elements, but this is not true. I think we should agree that orbital currents can be very large in titanium, in material which are light. I mean, you don't need to have a strong spin orbit in principle. Yeah.
But for instance, if we do an EPR experiment, like an electron paramagnetic resonance,
Yeah.
we measure the Zeeman splitting, we extract the G factor of the compound that we wanna see. If you observe something which is much more like than 2, the conventional 2, it's a good candidate for the quadruple.
Principle, yes.
Okay.
Yeah, that's a good point. Yeah.
So normally, what impact do you see of this surface magnetism on superconductivity? Do you see some impact, like?
Yeah, the question is how this magnetism is it talks with the superconductivity.
Yeah.
Yeah, I think okay, this is a good question, and it is a matter. So this is something which we are going to investigate. So that okay, at the zero level, you know, these if you have a magnetism, superconductivity is the best object to detect the tiny magnetism. So even 10 Gauss for a superconductor would be something which is making, right? So an impact, right? So this is let's say the zero order impact. It's just a magnetic field that is trying to penetrate. I mean, so the second order impact is that this is a weird electronic state, right? Which can couple to the superconductivity, and how we don't know. So we want to study it. So I can tell you that. So I think you. So you are aware about this. This experiment that Bina Kalinsky did on these TMD materials, where they have this weird anomaly of the vortex. So the point that, you know, there can be a hidden ordering like this one that you don't see. You cool down, you go through it, then you cool down, you enter the superconducting state, then you go up again, you cool down, and you see some anomaly. What is happening? This guy is ordering. Making domains, things, and the guy, the superconducting has to, but you don't know because this is a hidden ordering, right? You can have these loop currents underlying in your crystal, which at some point should coexist with superconductivity and make anomalies in the vortex lattice, in some magnetic response, because the superconductor is very sensitive. So I think that, for example, root rates, the fact that they measure this temperature semi breaking somehow is linked to the surface. But there can be more, I mean, more things going on.
Yeah, Andrea.
Thanks for a great talk. Question about the effect, relevance of the effect on sensor root at 113. So
Yeah, okay, so, yeah.
Can you imagine situations in which you know, maybe a low symmetry sensor root at 113 could present some of these quadruple order effects? I'm thinking concretely, there are some reports in the literature of 111 sensor thin films that have some anomalies in the size of the Bohr magnetron, and there was a discussion on transition to high spin, low spin. There was some controversy. I'm wondering if maybe.
No, I think that the point that you have to really make very thin, you have to get down to the monolayer to build up. I mean, already the belayer is actually, so Federico tried also the belayer and he didn't find anything. So something is really 2D like in the, so there is an object, I mean, or when you make, when you give this kinetic energy, so other instabilities, they can compete. So, but, so maybe, yeah, if you really go down to 1 or 2 layers, it might be interesting to look even at the 113, which is again, is like the same material, is the same structure. Okay, I don't know whether these are, because I think the 113 is tetragonal when it's monolayer, right? Becomes more tetragonal because it's the substrate.
Especially on STO.
Yeah, exactly. While this guy is orthorhombic, you know, this is probably also you have to choose a substrate to get it orthorhombic. Maybe then you get it. Maybe. Okay, it can be interesting, yeah. It's a challenge.
I was wondering, in these orbital loops, at some moment you make the calculations of the energy, and those that are out of phase are more favorable.
Yeah.
What elements in the Hamiltonian, or what is the energy scale that makes the system prefer this phase over the other one? Which is, there is a
spin orbit.
Spin orbit.
Yeah, when it's spin orbit is 0, they're degenerate.
Okay.
So the spin orbit is such that basically, okay, I don't know, maybe there is also more fundamental understanding. Yeah, these are currents, right?
Yeah.
So maybe there is a Ampere law for these currents that you prefer to make it anti-parallel instead of parallel. So, yeah, but this is spin orbit, yeah, this is, yeah.
I was wondering if the Chanteller interactions are weaker in T2G systems, but this is a Chanteller system in ways. Because
Yes,
it's a weak Chanteller system, but it's not relevant in this case compared to the spin-orbit coupling, I guess, no? Because I was wondering if Chanteller is playing a role, maybe you have some.
okay, the antenna, yeah, the antenna in T2G is smaller, I mean, there is there is no degeneracy. I don't see actually, also this is a metal.
Yeah,
No, it's a metal, you
Yeah.
don't have this, I mean, electrons are really fast, right?
Yeah,
So lattice is,
yeah,
it doesn't follow easily, I mean, it's.
yeah, so it's.
The lattice is low, but it's like, it's a metal, I think maybe, yeah, probably, yeah, in principle, you can get this object, I mean, in an insulating case. But then everything should go in the collective part, if you want, right?
Yeah.
If you think about something which is, which has been actually, something has been done, I mean, this type of ordering, you know, they are related to this, they can be also phrased in the context of multiferroicity.
Mhm.
Because this object is an object which breaks inversion and time, but it can preserve PT. So these are anapole-like ordering, which have been when you do this multipolar expansion for your magnetic state, you can get not with L but with a position with R. You know, this type of ordering which involve electric polarization, which is and they are not the same object because these objects are really dipoles. So not, but there is a connection. Maybe there is something which you can find, which can be related in the context of insulators with the multiferroics. But it's also something which would be interesting to look at. Yeah.
I don't know if there are more questions. In the chat line, there are no questions.
They're dead.
No, there are questions, I guess. No?
When did this paper came? I mean, it's a very recent one, huh?
Sorry?
The paper.
Yeah, the paper it appeared 2 months ago, a couple of months ago. Yeah.
Okay.
Yeah. So I don't know whether it's somebody on the.
No, because I don't see any.
Don't see anything. Okay.
Okay,
Thanks. Yeah.
More
Thanks.
questions here? No? Well, if not.
Last
we-
chance. No,
Last
okay.
chance. So thank you very much, Mario.
Yeah, thanks.
Remember that tomorrow we start the school 8:45. So see you tomorrow 8:45 Barcelona time, of course.
With more fun.
Okay, see you.
Thanks.
See
Yeah.
you
Thank
tomorrow.
you. Vabbè, comunque c'è creduto. Ma devi fargli la foto con il. Io faccio su, scusa.
Allora faccio con la foto io che cambiare, perché quella è una questione.
Sì, del.